Today we are going to continue on in chapter 18, talking about acids and bases. Um, so just sort of as a brief review, when we have an acid or a base, really what we're looking at is the concentration of our hydrogen ions and our hydroxide ions. We have a higher concentration of hydrogen, it's acidic. It's a higher concentration of hydroxide, it's basic. So, and as we started out yesterday, we kind of, well, not yesterday, the day before, it was, we started talking about how there are some acids that will literally melt your skin away. But then there's plenty of other acids that really aren't that big a deal. So what determines that? Well, largely, we can break acids into two groups, what we call strong acids and weak acids. Now, strong acids, even within strong acids, we can have some that are stronger than others. But strong acids, weak acids. Okay? And really, what the difference is. So if we have a strong acid, so hydrochloric acid is a strong acid. So when that happens, when we put this hydrochloric acid into water, almost all of this turns into this. Right? In fact, it's so close to all that we just say all of it. Everything that you put from here into water is going to dissociate into hydrogen ions and chlorine ions. Okay? However, if we have, well, let's consider a weak acid. Okay? Hydrofluoric acid. Hydrofluoric acid is a weak acid, and we still do get dissociation. Okay? We're going to have some of this, but we have a good portion that stays together instead of breaking apart. And that right there is what you need to understand about the difference between strong and weak acids. Strong acids completely dissociate. Weak acids only partially dissociate. So now, if you notice, we have these double-sided arrows, okay? Which means we're dealing with an equilibrium situation, which means we can write equilibrium constants. So if we look at this, we've got this equilibrium constant. And remember we said there's almost nothing of this left. This is a really, really small number. In fact, it's so small that pretty much everything is up here. Now it's not zero because, well, number one, that would make the math not work because you can't divide by zero. And it's, we know that it's not 100% zero, but it's so close that we can pretty much just ignore it. That's not true for the weak acids. have a significant amount of the acid that's still together. Okay. So writing these equilibrium constants, obviously that's exactly the same as what we've been doing for, this is the third chapter that we've been using them. However, we will make one small adjustment. When we're dealing with acids, we can call it a Ka. So anytime you see Ka, you know you're dealing with an acid. Okay? We call this the acid ionization constant. We have that. Now, we mostly only use a Ka for weak acids. And that has to go, or it goes along with the fact that, there's really not much of this at all. And so we can actually look at this. Okay, so if we said that we have 1 molar hydrochloric acid, pretty much all of that is over here, which means the concentrations of both of these are going to be 1 molar. So we can put those in there, and you don't really have to deal with the Ka. Much like the KSP. We don't really calculate a KSP for things that dissolve very readily because it just doesn't really make that much sense. So Kas are really primarily for weak acids, and they are going to tell us basically how much of this acid is going to dissociate. That's what the Ka tells us. How much is actually going to dissociate? The higher the Ka, well, the more it's going to dissociate, because that means we have bigger numbers up here and smaller down there. So basically, strong acid completely dissociates. And you put it in water and it just breaks apart. Because of that, however much you put in the water, well, that's what your concentrations of the H plus are going to be. For weak acids, only partially dissociates. So we use this equilibrium constant to figure out what these concentrations are going to be. So now, just like we can have strong and weak acids, we can have strong and weak bases. The good news is, it's just the same. Okay. If we have a strong base, sodium hydroxide, okay, put that in water, you're going to get sodium ions, hydroxide ions. We don't really need to do an equilibrium expression for this because it all does that. Okay. But if we have a weak base, okay, the example in the book is methylamine. Okay. And let's get one too many. Writing it as if it had already gone to the other side. Because here we have and we'll throw in water there to make a balance. So. Now, in this situation, okay, we can write a Kb, Notice we call it a Kb instead of Ka because we're dealing with acid, or we're dealing with a base now. We don't use the water in there because it's a pure liquid, and so it doesn't get included. Notice, whenever we have one of these, either a Ka or a Kb, we're going to either have this in there somewhere or that, which is important because remember, this is what determines whether we have an acidic solution or a basic solution. Okay. So this section is pretty straightforward. Basically, if it's a strong acid or a strong base, whatever you're starting with, when you mix it with water, it completely goes away. Okay. In this case, if this were a strong base, notice it doesn't break apart, but all of this would have pulled that hydrogen off the water. Okay. Remember, we're dealing with Bronsted-Lowry. Now, this is definitely an Arrhenius base. This one is not. This one you have to use Bronsted-Lowry. And so it's not just that it breaks apart necessarily when you're in bases, but you have to say, okay, everything that we started with went to the other side of the reaction. Okay. Which, once again, with concentrations, okay, even if it's not an Arrhenius, okay, well, for every one of these, we're going to get one of these. So even if we have to think of it in the Bronsted-Lowry, the concentration here is really just the concentration of this that we started with. So. But if it's a strong acid or a base, completely reacts. Okay, we don't have any of our starting material left. If it's a weak acid or a base, it only partially reacts, and so we can figure out these K values. And that tells us sort of how far equilibrium has gone. So that's strong and weak. And that's section 2. It's a short section, pretty straightforward. So we're going to go straight into section 3 now. And section 3 introduces the idea of pH. pH. You've probably heard that somewhere, pH. Basically, pH tells us, are we dealing with an acid or a base? It measures the hydrogen ion concentration. Now, in order to get to where we can understand pH, we got to take a couple steps. And the first thing is going back to this. Now, we said water can do that by itself. Okay. It's called the autoionization of water. Anyway. Now, after doing some research and figuring things out, what we found is that water, and this is specifically at 298 Kelvin, okay, but in water at 298 Kelvin, the concentration of our H plus ions is 1.0 times 10 to the minus 7 molar. So in every liter of pure water at 298 Kelvin, we're going to have 1 times 10 to the minus 7 moles of hydrogen ions. Measuring the hydroxide, we figured out it is also 1 times 10 to the minus 7. So if we set up our K expression, now this is a pure liquid, so we don't include it. So all we have, H plus and OH minus. Normally we put that underneath, but because it's pure liquid, we get rid of it. Now this is a special one. We call it the KW. W for water. And using these, we can establish that KW 1.0 times 10 to the minus 14. So this right here is actually an important number. We're going to use that quite a bit in this chapter. And basically the way that we use this, so if we look at Le Chatelier's principle. So let's say we have pure water and we add some hydrochloric acid, or really any acid. Doesn't have to be a specific type. We've added acid. What's that going to do? Well, it raises the amount of hydrogen ions. Okay. But we know that KW, when you multiply the concentration of hydrogen ions and hydroxide ions, it is going to equal this number, 1 times 10 to the minus 14. Okay. So if this number goes up, well, this number has to go down. Okay. And like we said, you know, if it's a strong acid, we know how many hydrogen ions we added because it's just the concentration, however many moles of that acid we added. So what we can do, we can say, okay, well, we know the concentration of this. We can use this equation to figure out the concentration of that. Okay. If you know one of these, you can always calculate the other. Okay. The example problem that it gives about this, okay, it deals with a cup of coffee. And it says that the hydrogen ion concentration in a cup of coffee, 1.0 times 10 to the minus 5th. Okay. So we know that this is our hydrogen ions. And it says, what is the hydroxide ion concentration in the coffee? And then it asks, is the coffee acidic, basic, or neutral? So we know this. We know this. So we can say KW equals hydrogen ion times hydroxide ion. We want to know what the hydroxide ion concentration is. So we solve for that. Get this. Then we just put this in right here, that in right there. Just divide. And it's pretty straightforward. Gives us that 1.0 times 10 to the minus 9. And so now we can look at this and say, is it acidic, basic, or neutral? Remember, the conditions are if there is a higher concentration of hydrogen ions, it's acidic. There's a higher concentration of hydroxide, it's basic. And if they're equal, it's neutral. Well, hydroxide, 1 times 10 to the minus 9. Hydrogen, 1 times 10 to the minus fifth. This number right here is bigger. 10 to the minus fifth is bigger than 10 to the minus ninth. And so you have more hydrogen ions, which means it is acidic. Okay. Doing this, like I said, we're going to use that quite a bit. Okay. All right. So now let's get into pH. So pH, like we said, it's a measurement of the hydrogen ion concentration. Now to calculate pH, pretty simple. Take the negative log of the hydrogen ion concentration. Now, this is why you need a scientific calculator, because you need something with the logarithm function. Honestly, you don't need to know what a logarithm is. We can save that for your math classes. I'm going to teach you how to work with it. And that's really all you need to know is how to do some basic things with it. One thing that you need to understand, though, this is not, we're not multiplying. This is not a multiplication. The logarithm is a function, which means we take a value and put it into that, and it crunches it, and it gives us a different value. Okay, so you can't say, okay, well, we're going to divide by log. Okay? That doesn't work. You can't do that. Okay? Logarithm is its own function. There is a way to get rid of that log, which we'll go over in just a little bit. But really, you find the log button on this calculator. It's right there. Push that, put whatever number you need to put in, concentration, and it gives you the answer. Okay. So that is how we calculate pH. We take the log of whatever our hydrogen ion concentration is, multiply by -1, and that gives us pH. We have a very similar thing for the OH, negative log of the hydroxide ions. Okay. So the pH scale. The pH scale runs, and also this is true of the pOH scale, but we're going to discuss the pH in the first part. So it runs from 0 to 14. Okay. From 0 to 7. This is where our acids are. And from 7 to 14, where our bases are. So if you put your concentration here and you get a pH value between 0 and 7, you're dealing with an acid. You do it and you get a value between 7 and 14, it's a base. If it is exactly 7, that is neutral. pH 7 is neutral. The further away from 7 you are, the more acidic or basic it is. Now that makes sense with bases here, okay? Because the number's getting bigger. But you have to stop and think about acids because it's not necessarily a natural way to think that a number getting smaller is getting more acidic. So really you have to stop and think, the further away from 7 something is, it means it's more acidic. Okay? It's more acidic. So, Another key piece of information that we'll use, pH plus pOH equals 14, always. Okay? So if you have something that has a pH of 2, okay, it's an acid, has a pH of 2, the pOH of that solution will be 12. If something has a pH of 8, the pOH is going to be 6. All right. If you add pH and pOH of the same solution, it will always add to 14. There's a mathematical reason for that. It has to do with the KW. Whether or not you can see the mathematical link is fine. You don't need to, as long as you can remember this. Okay, pH plus pOH equals 14. Trying to remember if I put that on the front of the test. Okay, so I don't have this, but that is on there. The pH equation is on there, which should, just have to remember that pOH, I just have to replace that. And I also give you the KW expression and the value. So there's a lot of really good information with acids on the front of this test. So anyway, so let's work with this a little bit, just so you can see how it works. Okay. Now this example problem, honestly, I don't really love the example problem because it says, what's the pH of a neutral solution? I mean, we know that it's 7. So we're going to actually do one of the practice problems instead. We're going to do this first practice problem. Calculate the pH given that the H plus concentration is 1.0 times 10 to the minus seconds. All right, so we say pH is the negative log of H plus. So the negative log of 1.0 times 10 to the minus seconds. Okay, once again, all we have to do, go to our calculator, take the log, 1.0 times 10 to the minus second. And so just that gives us a negative 2. But remember, it's a negative right there, which turns it into a positive. So pH is 2. Okay. And that's really, what we're dealing with is whatever this is, just put it in the calculator. Okay? That's what we're going to need to know. Okay? So honestly, it's pretty straightforward. Pull out your calculator, you put that value in, make sure that you remember that it's negative, and you're done. Okay. We'll do example problem 3 because that one is a little bit more like what we'll experience in homework and tests. So, a cow is being fed straw and hay that has been treated with ammonia. The addition of ammonia to animal feed promotes protein growth in the animal. Another use of ammonia is as a household cleaner, which is an aqueous solution of ammonia gas. Okay. A typical cleaner has a hydroxide ion concentration of 4.0 times 10 to the minus 3 molar. So it tells us 4.0 times 10 to the minus. So it tells us that. Okay. Calculate the pOH and pH of a cleaner at 298 Kelvin. All right. Well, we know that the pOH is the negative log of the hydroxide ion concentration. So the negative log 4.0 times 10 to the minus third. We just put that into our calculator. That is going to give us a value of 2.40. Okay. Now, that is the first part. We also want to find the pH. Well, once you've got pOH, the easiest way to do it, it's not the only way to do it, but the easiest way to do it is to say, okay, pH plus pOH equals 14. So the pH equals 14 minus pOH. So 14 minus 2.4. Okay? And that is going to give us a value of, I was wondering, I was looking at it and thinking, am I doing the wrong problem? Because I was looking at a different problem. Anyway, it gives us 11.6. Okay. So now we can look at this and say, does it make sense? Okay. A pOH 2.4, that is basic, okay, especially because we can say the corresponding pH is 11.6. Basically, anytime you're dealing with the pOH, everything flip-flops. So below 7 is basic and above 7 is acidic when you're dealing with pOH. So just keep that in mind. It might be easier as you're getting started to just stick with pH and say, okay, well, this is pOH. I don't really want to mess with that, but I can see that the pH is 11.6, which is definitely basic. So, okay. Like I said, there's another way you could attack this. It's not the easiest way, but it is valid. You can go back to the KW and calculate the H plus concentration based off of this, and then put that into the pH equation. It's an extra step. It's more work in my mind, but it will get you the same answer. So anyway, now we want to go the other direction. Sometimes we're given a pH and need to calculate the concentrations. So this is example problem 4. So it says, what are the hydrogen ion and hydroxide ion concentrations in a healthy person's blood that has a pH of 7.40? Okay. So it tells us pH equals 7.40. Okay. So we want to know the concentration. Well, we still go to this same equation. Okay, we can still say pH equal the negative log of the concentration. Okay? Because that's how we relate these two. But now we need to solve for the concentration. And remember, we can't just divide. That's not how it works. What we have to do, first we move the negative. Okay, our algebra, so negative pH equals that. Okay, that's our first algebraic step. And now, the opposite of log, because remember, that's what you have to do. If you're adding something, you subtract it. If you're multiplying, you divide. You need to do the opposite. Well, the opposite is 10 raised to that power. So we have to 10 to the power of whatever it is on both sides. Okay. So now that cancels out. So 10 raised to the negative pH equals that. Okay. So once again, if you understand logarithms, that makes sense. If logarithms are new to you, just memorize this. If you want to get rid of log, 10 to the power of. One thing that will probably help you, calculators tend to put opposite functions on the same button. So if I wanted to get rid of a log, I do second and then push the log button, and that has a 10 to the power of. So that should help you, get familiar with your calculator. The opposite buttons are typically, one, you've got the log, and then shift with the same button is the opposite function. But anyway, like I said, if you understand logarithms, great. If you don't, just memorize that to get rid of it, you have to use this 10 to the power of. Okay, so to find the concentration here, you take 10 and raise it to the negative 7.40. And once we do that, now the book calls it the anti-log. To be honest, I have really seen very few sources that call it anti-log. Just 10 to the power of. I find that more common. But just so you know, the book does use the term anti-log. Anyway, which gives us a value of 4.0 times 10 to the minus 8. Okay. It also wants us to calculate hydroxide. Now, once again, there are two different ways that we can do this. We can take this number and throw it into our KW. And that's completely valid. Or the way this example problem does it says, okay, the pH is 7.4. That means our POH has to be 6.6 because they have to add up to 14. And then we just throw that in here. POH equals the negative log of our hydroxide concentration. We do the same math. We end up with 10 raised to the negative POH equals the hydroxide concentration. And we do 10 raised to the 6.6, the negative 6.6. And that gives us our concentration of 2.5 times 10 to the minus 7. That does show us that our hydroxide concentration is a bigger number than our hydrogen concentration, which tells us that it's basic, which is what we would expect. So that's the way the example problem does it. Like I said, if you wanted to say that KW is this times this, you could say, if we wanted to find this, because we already have done this, so KW divided by H plus, which is OH minus, 1.0 times 10 to the minus 14, divided by this right here, 4.0 times 10 to the minus 8. And then just to verify, we'll put it in the calculator. So 1 times 10 to the minus 14 divided by 4 times 10 to the minus 8. and it does indeed give us 2.5 times 10 to the minus 7. So, for me personally, I probably would do this. If for no other reason than I just figured out this number, and so it's in my mind, and I would have just said, hey, I can throw that number into an equation, have it. Either way, gets you the same answer. So there's no better way to do it. It's personal preference. So, the last example problem is calculating Ka from the pH. We're not going to go through that. It's pretty straightforward, but I don't give you any questions about that on the homework or the test. It's just, has enough moving parts that I just kind of say, okay, we don't need to do that particular one. But like I said, it really is pretty straightforward. All you do is this step, and then you can do that. You have to write the equilibrium expression, and then you can put that in, and it's a little bit of math here and there, but anyway, we just sort of ignore that part of the chapter. So I'm sure no one's going to be too upset about that. Anyway. So that is the end of section 3. And I purposely didn't do the litmus thing like I said I would, because that actually is going to work really well with section 4, neutralization, because we're going to talk about neutralization, and we'll also talk about the lab that we have coming up. So we'll talk about that next week. So for now, I will stop talking and start on some homework. Yeah.